Hello everybody and welcome to our first real lecture about artificial intelligence for biotechnology. In this first lecture, I'd like to give you an overview about the field of artificial intelligence and machine learning, where's the difference between these two terms, and about different types of machine learning models, types which we will also look at in our lecture, and about recent developments and applications in these two domains. So the first thing we should ask ourselves is, what is artificial intelligence? And therefore, I just like to give you a definition. So artificial intelligence is any intelligent machine, software or technique that perceives its environment and makes decisions like humans would do. That's very general now. That could be a lot of things. And within this domain of artificial intelligence, there's a subdomain. And this subdomain is called machine learning. So machine learning is all about constructing and studying systems that can learn something from data. So therefore, it's very important that we have data that we can learn from. And that's the difference to artificial intelligence. Artificial intelligence is much more. Artificial intelligence doesn't restrict itself to data, while machine learning is restricting itself to data. So we like to construct and study systems that can learn from data. I will come to this back in a few minutes again. And within the domain of machine learning, there's a very recent domain that many of you might have heard of, which is called deep learning. Deep learning is a branch of machine learning that uses a specific model that is very often used in machine learning, namely neural networks, to learn from data. So it's just a specialized subdomain in the field of machine learning. So machine learning is much more than deep learning. This course is all about the foundations of machine learning. So what will we learn in this lecture? This lecture we will learn what is AI and machine learning, what are the problems that can be solved with machine learning, and what are the different machine learning problem types that exist and that can be handled. So let's look at this phrase or at the definition of machine learning again. So machine learning, we said, is constructing and studying systems that can learn from data. So what do I mean with this? So let's look at a classical algorithm. So here, a classical algorithm could be, for example, a recipe. The recipe, how to make pizza. So we have an algorithm, which is our recipe, exactly defines steps of what we have to do. And then we have ingredients. And the ingredients are the input for our algorithm and the output is the pizza. So very well defined steps for specific inputs and we get an output. Machine learning, however, has the following rationale. So in machine learning, we have many pizzas. And we know for all the pizzas the ingredients. And then what we like to find is, based on the data, based on all the pizzas that are out there and the ingredients which we have measured in our data set, we like to fit it into a model and we would like to predict the recipes for these different pizzas. So here we really like to find the recipes or predict the recipes, and here we have the ingredients, the recipe as the algorithm and the pizza as the output. Here we like to learn from data. So when to use machine learning? There is no real need if we like to compute our payroll or to compute the mean of a series of numbers to learn something. There is a specific defined recipe that we have to follow. If we have to compute our payroll, we know exactly the steps that we need to compute the payroll. Or if we like to compute the mean of a series of numbers, we exactly know, based on the mathematical definition of the mean, how to compute the mean. So when is learning used? Learning is always used when data is cheap and abundant. So what do I mean with cheap? Cheap is relative here. So for example, data can be also expensive. But sometimes it's better to buy this or produce this expensive data because in many cases expert knowledge is more expensive. So if we like to, for example, get information about data and we like to label data, we need some specific expert knowledge. And this expert knowledge is in most of the cases expensive. And expert knowledge is also rare. So when data is cheap and abundant and expert knowledge is expensive and rare, then we would like to learn from data. So when is this given? For example, that is when human expertise does not exist. Where does human expertise not exist? Mostly in scientific research. So when we like to learn or predict a new chemical structure, or we like to design a chemical structure that has certain properties, then we don't have maybe the expertise for this. We might have some prior knowledge, but we not necessarily know how to do this. And then we could use machine learning models to learn from existing data to maybe predict chemicals that have similar properties. Learning is also used when humans are unable to explain their expertise. Where is this the case? For example, in computer vision. When we see things, so when we see around in the landscape, then we directly in milliseconds recognize the objects that are there. That specific thing is a car, a specific thing is a cat. We can make sense of it. Computers just see pixels. And humans can't explain how they know that this is a cat, how this works in the brain. So therefore, machine learning is very important. Also for speech recognition. How do we recognize sound? And it is used when existing solutions are expensive. For example, if we like to determine the three-dimensional structure of a protein, this is a very complex and very expensive task because either we make crystals out of the proteins and then we go to an X-ray to shoot with electrons on the protein to get the three-dimensional structure. That's expensive and is very needs a lot of expert knowledge. And in these cases, we very often use machine learning. So what's the goal now of machine learning? The goal is that we like to find a model that is a good and useful approximation of our data. And the sub-goals are that we like to learn a model that generalizes well on new data, and we have to evaluate whether the model generalizes well on new data. Why do we have to do both? The learning and the evaluation, because predictions are hard, especially about the future. That was already a sentence which Niels Bohr said. So it is easy to build models that perform well on our training data, on the data we have at hand, but how does it look like? How do they perform on new data they have never seen? So that's why we have to learn a model that generalizes well on new data, and we have to also evaluate whether they generalize on new data. What I exactly mean with generalization, I will come to at a later point of this lecture. So let's look at some types of machine learning systems and machine learning models. What are these different types? Here I will show you three types of machine learning models: the supervised learning, unsupervised learning, and reinforcement learning. These are the three main areas of machine learning. And I first like to explain you what is supervised learning. So supervised learning is all about learning a function from labeled data to make predictions. And therefore we distinguish between two types of supervised models. One is called classification and the other one is called regression. In classification, we like to make discrete predictions. And in regression, we like to make continuous predictions. What I mean with this, I will explain you in two examples the next few slides. So, regression. In regression, I said we like to make continuous predictions. So let's say we like to predict the prices of a house. I also said before, in supervised learning, we need labeled data. So if we look at the sentence here again, supervised learning is all about learning a function from label data to make predictions. So we would like to make predictions in this example. So we would like to predict the price of a house based on the size of a house. So we have here some data, different houses, and we know the sizes, and the label therefore is the price. So the label is the variable which we like to predict. So in this example here now we have different houses, some small houses and the price, and some large houses and the price as well. So if we now plot this in a two-dimensional plot, we see here at the x-axis the flat size in square meter and the price in dollar. And you can see based on the dots here that there is some relationship, a linear relationship. So what we try to do in a regression, we like to learn a so-called decision function that describes our data as well as possible. And then we would like to know for a new flat, for which we only know the size, we like to know what's the price for this new flat. And then we can look at this regression, at this decision function which we have learned, and see where the point lies on this decision function to predict the continuous label, in this case the price of the house. So this is called regression. That was now a very easy example. We will look at models which can be used to do regressions. The simplest one is a linear regression. So what are different applications of regressions? So regressions are used, for example, in stock market predictions or in algorithmic trading. So there we would like to know the price of a certain share. We would like to predict this, that we can buy the shares before others buy them and make profit out of it. Or it's also used for income prediction. Very often when we like to start a new job, we would like to know how much will I earn? What will be my income? And then I can, based on some information, I can try to predict the income. Other things, for example, in biotechnology is drug development. So for example, what is the binding affinity of a certain drug and its target? In precision medicine, which dose of a certain drug does a patient need? This can be predicted. This is a regression task, for example. Or in breeding, either in plant breeding or when we work with bacteria, we would like to predict the phenotype of a plant or a bacterium based on its genotype. For example, how long will it take for a plant to flower, or what is the reaction time of a certain bacteria? Or also, for example, in internet applications, the click predictions or load predictions. I'm very often interested in how many people will click on a certain ad that I can earn money with it. Where do I have to place the ad that the people will click on it? How many people will share my article on social media? Or will my service, or how many people will use my service at a certain time point? For example, if you watch Netflix, then they would like to predict, or they're predicting at which time points people will use the service more or less, that they can scale up their systems dynamically. So these are typical regression applications. So now let's look at classification. So I bring a small example again. In classification, we would like to predict a discrete label, we said before. And what are discrete labels? For example, if you look at your emails, you would like to know which of the emails is spam and which of the emails is no spam. So what we try to do in classification, we try to learn also a decision function that separates these two classes, and that on the one side of the decision function are only emails that are spam, and on the other sides are only emails that are non-spam. And then the prediction task is that when you get a new email, you would like to classify it on which side of the line this decision function is this email, so can it be classified as spam or as non-spam. This was a very easy example and one of the first ones, so I'd like to show you now some other examples and domains where especially our group is also working on, and one is, for example, precision medicine. So very often you have a group of patients and you have a certain drug. but not all people react to this drug the same way. So some people might respond to the drug, some people might not respond to the drug, and some other people, some subgroup, might have severe side effects. And before we subscribe a certain drug to a certain patient, we would like to know, can we classify this patient into a responder for this drug, into a non-responder, or will this patient have severe side effects? That's called precision medicine or personalized medicine, and there's a lot of research going on. Also, our group contributed to a Nature Biotechnology paper where we tried to predict human population responses to toxic compounds. Another example where we are very active in is, can we predict the phenotype of a plant or of a bacterium? For example, here you see the different flowering colors, yellow ones and blue ones. Can we predict the flowering color based on the genetic architecture of these individuals? Or if we have genotyped many bacteria, can we predict specific phenotypes or products this bacteria will produce? A very recent example from my group was done by Nikita Gente, a master student in our group, which is now a scientific employee, PhD student. He investigated if he can do germination predictions using artificial intelligence and computer vision. So what he did is he created thousands of images of seeds in a petri dish, and he then wrote a machine learning algorithm that first of all tries to identify in the image where is one of the seeds, which sounds like an easy task because we see, okay, there and there and there are seeds, but for a computer it's highly non-trivial because a computer only sees individual pixels. It doesn't know what these pixels mean. So he first wrote an algorithm to find or to predict, do a region proposal, where are the seeds, and then he predicted if the seeds start germinating or not, and that you can see when here the boxes change to red, then the algorithm starts to predict that the seeds start to germinate. Other domains or other classification applications are, for example, deleteriousness prediction. That's also from the field of biotechnology or biology. So there we like to predict if a certain mutation in a protein leads to a deadly or damaging effect. Face recognition would be in the field of computer vision. There we like to identify faces independently of the pose, the lighting, the occlusion, makeup or hairstyle. Or also in sound recognition, so which song is currently played in the radio or who spoke the following sentence. These are examples like everybody of you knows Shazam, for example, where you can listen 12 to 12 seconds of music, and then it will tell you which interpret and which song it is. These are classical classification problems. So to summarize this, supervised learning is all about learning from labeled data. We have data and we have a label for it. If it's a discrete label, we have a classification problem, and if it's continuous labels, we have a regression problem. And in a regression problem, we try to fit a line to the points, and in a classification problem, we like to find a decision function that separates the two classes or the three classes. And then when we have new instances in regression, we try to predict the value of this new instance. In classification, we'd like to predict the class of this new instance. So, supervised learning. In supervised learning, we have a ground truth. We know the label of the data, we know the data. And this way, we also get, when we learn with this data, a direct feedback. So we know in the moment when we do something wrong that we did something wrong, and it's used for prediction. The next subdomain I would like to show you what type is the so-called unsupervised learning. So unsupervised learning, there you have unlabeled data. So we don't have a class label, or we don't have the continuous label. So we maybe only have the sizes of the houses, or we only have the have other features, but we don't have class labels or continuous labels. So in unsupervised learning, we try to find, hidden structures in the data. So we like to find, for example, that these data points belong to each other, these data points belong to each other, and these data points belong to each other. And then we have to look at these clusters, so that's called clustering, to make sense out of these clusters. And maybe if we look a little bit closer at these instances that are in these different clusters, that we find out that here we only had plants, animals, and bacteria. That's just a toy example, but where is this used in industry or in applications? For example, in customer segmentation. So in customer segmentation, we try to find groups of customers with similar buying behaviors. Or also in medicine, it's used, for example, for cancer stratification. So we like to find groups of patients with similar pathologies or with different subtypes of cancer. So sometimes we can't say, okay, this is lung cancer, because lung cancer also have different subtypes of the lung cancer. So we like to find these different subgroups using clustering. Or also, for example, in text analysis or in text mining, so we like to find documents based on words they contain to identify common topics. Another example in dimensionality reduction, in unsupervised learning, is dimensionality reduction. So very often, especially in practice, we have samples, and for the samples we have thousands, millions of measurements. That's very common in genetics. Then you have 1 or 2 individuals and you have millions of mutations for them. What we try to do in dimensionality reduction is we like to find a lower dimensional representation of our input data. For example, here in this three-dimensional plot here, or you see here this Swiss roll that usually can be showed in a three-dimensional plot. So we have 3 dimensions, and then we like to find a lower dimensional representation that we can illustrate in a 2D plot. So here we try to find this lower dimensional representation that reduces the data to less dimensions, but preserves the information and the content of the data as much as possible. So when is dimensional reduction used? It is used to reduce complex data. So very often we have too many dimensions, and then some algorithms don't work anymore, or the speed suffers. So the algorithms are slow, or we have too less computing resources to analyze the data. Then we have to reduce this data such that we can do sensible or meaningful data analysis with it. Very often, dimensionality reduction is also used to visualize complex data, that we can project 10 million dimensional data sets down to just 2 or 3 dimensions to get some interpretation. And it's used to also reduce noise or to remove redundant features. So if there is very often in this data set redundant information or noisy information, and this we can reduce using dimensionality reduction. And thus, we can also use it for data compression. So how can we store images, for example, on a hard disk without using too much disk space? Therefore, we can use dimensionality reduction to remove non-important information from the images. And there I like to show you a very interesting example which was published in Nature in 2008. So what has been done here? So here you see a lower dimensional representation of 3,000 Europeans. So what has been done in this study? They used 3,000 Europeans and they genotyped them. So they tried to find out what are the differences in the genotype between these 3,000 Europeans. So they had approximately 500,000 genetic differences between the 3,000 Europeans. So what you have here is you have 3,000 Europeans times 500,000 dimensions. They then just did a simple principal component analysis. You will learn about it later, and you don't have to understand the concept of a principal component analysis right now. But what they did, they just plotted the first principal components. So you get a 2-dimensional plot, you get here a coordinate system, and then they highlighted all the individuals, so each single dot here is one of the 3,000 Europeans. And then they highlighted these different individuals based on their origin, where they were born. And you can see, based on this color coding here, that this very much looks like the European landscape. If you look here at the European map, then you can see here this information and this principal component analysis. So, based on the genetic differences of 3,000 Europeans, we can draw the European map. And this is very interesting because, and this the authors did it as well in this Nature paper, they learned a predictive model to predict the latitude and longitude of each individual only based on their genetic differences. And this worked pretty well, so up to a few hundred kilometers accurately, they could predict where a specific individual was coming from based on the genetic differences. And we also did the same in Arabidopsis thaliana, that's a plant, and in this we even could show that we can predict up to 2 kilometers accurately where a specific plant was grown. So, unsupervised learning, here we don't have a ground truth because we don't have a label. This way we also don't get direct feedback, but it's very helpful to find hidden structures in the data or to reduce the complexity of the data. The last domain is reinforcement learning. Reinforcement learning is very much different from supervised learning and unsupervised learning. And from some people, it's also considered the holy grail in machine learning or in artificial intelligence. So what is reinforcement learning? Reinforcement learning is doing a maximization, a long-term maximization by trial and error. So what do I mean with this? Let's look at an example. We have here an agent and we have a specific environment. We have some actions, we have observations, and from the environment we also get an event. So, an example here. Let's say we have here a computer environment. Our actions are the keyboard of a controller, so we can go right, left, down and up. And our observation is how Super Mario is navigating through the landscape here. And of course from the environment we also get a reward. How is the score of Super Mario? And what we try in reinforcement learning is to learn an agent that can more or less navigate or play Super Mario without losing. And what do we try to achieve here? We like to maximize the long-term reward by letting the computer play this game as much as often by maximizing this reward here, so the score of Super Mario. And that's a toy example that has been done. For example, here you can see Super Mario in the first generation of the network. It just more or less is running in a straight line, nothing is happening, and everybody could do this. But if you let it train and play the game more often, the computer will learn some actions. And after 34 generations, the agent has learned how to play the game pretty well without losing and by maximizing this fitness score here. So that's how reinforcement can be used for computer games. And even if this is a toy example, a very recent publication in Nature from October 2030 was about a reinforcement algorithm that mastered to play StarCraft 2 by using multi-agent reinforcement learning. So here in this Nature paper, the company DeepMind showed that they can learn on artificial intelligence using reinforcement learning that can beat almost every human player in the world. Other more useful examples like playing computer games is for example smart home automation. So there we use reinforcement learning to anticipate human needs. So we like to learn when is a human being adjusting the temperature of a room. And then it learns the behaviors of the human being and tries to avoid that the human has to readjust their thermostat. Another example where reinforcement learning is very successful is in robotics. There is a company, Boston Dynamics, and for example here they learned a robot to do a backflip. It sounds easy, but it's a super complicated task. However, reinforcement learning very often also leads to failure. So in reinforcement learning, we have a decision process. So we like to learn a strategy based on a reward system, and here we like to learn the series of actions that is needed to maximize the long-term reward. And there are many more subtypes of machine learning. There is semi-supervised learning, co-training, federated learning, adversarial learning, and so on. A lot of other subdomains which we can't look in this course. So in this course, we will mainly look at supervised learning and unsupervised learning, and the other domains we won't be able to cover in this first introductory course. And now at the end of the lecture, I'd like to give you some more examples, some recent developments in the field of machine learning that are very fascinating, but could be also shocking and make you think. So one of the first examples I would like to show you is artistic style transfer. So this is a paper which was published by a group from Tübingen. So Tübingen is one of the hotspots for machine learning. They are some of the smartest people in the world to develop new machine learning algorithms, and they developed a very interesting algorithm. So what you can see here on the left is an image from the city of Tübingen, and here you can see an image from Van Gogh. And they learned an agent or a neural network that analyzes or tries to learn the style, the painting style of Van Gogh, and then they applied it on the image of Tübingen. And then you can see, okay, they can then repaint every image they would like to with the style of Van Gogh by learning the style here. There's also a web page that you can use to upload any picture you like to apply the style of this picture on a different other picture. Another example from 2019 was the following. So here you can see a lot of different faces. But these faces don't exist at all. These are all fake faces. None of the faces exists in the world. So they learned an algorithm which looked at millions of human faces and learned features that make a face. And then they used this model to generate new fake faces. And all of these things look pretty amazing. Also the detail which you can see in these different images, but none of these images or faces exist at all. Another example from the field of biotechnology is protein folding. So we would like to learn based on the genetic information, based on the amino acid chains, how the protein folds. And that's a very complicated task, and there's a lot of research going on also from DeepMind that published the StarCraft paper. Other example is, for example, here, this real-time multi-person 2D pose estimation. So they learned algorithm or artificial intelligence that can do pose estimations based on a video stream. So why is this useful? Pose estimations are, for example, used by car companies, maybe in the future, that they, based on a camera, can identify if a specific person is coming to the car and if this person is the owner of the car, because the pose or the walk of certain persons is like a fingerprint. And based on this fingerprint, the cars could be then already adjusted that the user has his favorite seat position or so on. But it might be also misused by specific governments to identify specific people in a video stream, even if they cover themselves. Another example, very prominent one, was where they used artificial intelligence to do lip reading. So here they just had a video stream of a person speaking, and they tried to predict based on the video stream what the person was saying. A very recent example, also from researchers from the Technical University of Munich, was this deep video portraits. So here on the left side, you see a video stream of a person, and on the right side, you see a different person. So, for example, on the right side, this could be Obama, and on the left side, this could be you, and then you do some movements, and the picture or the video on the right behaves like you. And they showed that there one can make really serious stuff, and that one can manipulate videos or also detect manipulations of videos. Other examples based on biotechnology is, for example, this example. Before I joined the TUM Campus Straubing here, I was working for a small biotech startup, which is now bought by a huge company. And there we try to make liquid biopsies. So we try to take blood samples, and based on the blood samples, we try to predict if a certain person has a specific type of cancer or not. And in this example, we were concentrating on non-small cell lung cancer, and especially on a specific mutation, which is called T1790M, which only appears after treatment. So this is a resistance mutation that appears after the patient is developing a resistance against the treatment. And based on the blood sample of a patient, we could, with a very high precision, predict if this, more or less, this treatment failed or not. So if he developed a resistance or not. And the other example is in the field of statistical pattern mining. So there we look at millions of positions in the genome, and there we try to find genetic variants that together can explain the phenotypic variability. So this have been just a few examples about recent developments, and in the next lectures we will then learn about supervised and unsupervised learning. So what should you know? You should be able to define machine learning. You should be able to define the goals of machine learning and understand what is generalization. And you should, if you get a problem, you should decide if this problem can be solvable with machine learning or not, or is it a typical machine learning problem or not, and decide which problem it is. Is it a supervised problem or an unsupervised problem, for example? That brings me to the end of this introductory lecture. I also uploaded the next video, which is a hands-on to give you some more details about NumPy, which is an important library that we need to implement some of the machine learning libraries. So thank you for your attention, and see you